Hocam tüm observable'ların permission olması bir postulat mı? Tüm observable'ların permission olması bir postulat mı?
Well, you see, what we want is, what we measure is a real number. So we are saying, we are postulating that the observations correspond to eigenvalues of operators. So the operators that correspond to observables should have all real eigenvalues. Well, that's basically the definition of permission.
Tüm permission'ların observable olduğunu söyleyebiliriz.
Not really. But I mean, for example, look at this n operator. Can we observe n operator directly? Can we count the number of phonons? Not really, but we measure the energy. But energy is related to the number operator. So is the number operator observable or not? I can relate it to something that can be directly observed. So I will say that it is observable. So, I mean, in all the cases that I can think of, the Hermitian operators, they are either directly observable or related to observable quantities. Or maybe...
How do you measure energy?
Well, it depends on your system. So, for example, in particle physics, what we measure is the particle, it hits an object, and we measure how much energy is transferred to our system. So that's the measure of the energy. Or if you have a charged object, you put it in a magnetic field. If you put it in a magnetic field, it will follow a trajectory. Well, the radius of that trajectory is related to the momentum. Once you know the momentum, you can drive the energy. Or you can just have your system as a calorimeter. It measures the temperature, let's say, or the heat stored in your system. You just send your particle into that system, so it increases the heat, and hence, by measuring how much heat, how much additional heat is given to the system, that should be the energy of your initial particle. Well, let's see, we had defined these states, but we didn't yet talk about their, both the alpha states and the energy states. But what about their wave function, the position wave functions? If you remember the position wave functions, we had defined them in this way. So this is equal to psi n of x. So what are the wave functions? Now let's start with the ground state. We know that the psi 0 of x, let us look at this one. A, this matrix element is 0. That's the definition of the ground state. A acting on this 0 ket gives me 0. This is not the coherent state 0. This is the number ket 0. But you see, A has the definition 1 over, let's say, square root of m omega over 2 h bar x plus I p over square root of 2 h bar omega m, acting on the ground state. And okay, these are my operators, x and p, and the x in the bra is the position. It's a number. It's like 1 centimeter, 3 centimeters, etc. Well, we know how the x operator acts in this on the position eigenkets. So this is equal to square root of m omega over 2 h bar x multiplying x0. We also know how the momentum operator acts. So plus I over square root of 2 h bar omega m 1 over h bar over I del over del x x0, this should be equal to 0. Well, these i's cancel, so I have square root of m omega over 2 h bar x multiplying psi 0 of x plus square root of h bar over 2m omega, the derivative of psi 0 with respect to x, this should be equal to 0. Well, the nice thing is this is a first order differential equation which will be easy to solve. Derivative of psi 0 with respect to x will be equal to m omega over h bar minus m omega over h bar x times psi 0. Well, what is the unit of m omega over h bar? Or the unit of h bar over m omega? It's length squared, meter squared. Now let me define x0 as square root of h bar over m omega. So it's some characteristic length of my system. So the derivative of my ground state wave function with respect to position is just minus x over x0 squared psi 0. Well, you can solve this differential equation. Psi 0 of x is equal to some number times e to the power minus x squared over twice x0. This is our ground state wave function. Well, let us determine this normalization factor. Yes, the normalization will be fixed by the requirement that this integral dx psi 0 of x squared should be 1 dx. Well, psi 0 squared is n squared times e to the power minus x squared over x0 squared. X goes from minus infinity to infinity. This should be 1. 1 should be equal to, do we remember this integral? In this case, alpha is 1 over x0 squared, so it's just x0. So this tells me that n, this normalization, I can choose it to be real. The phase is not important. This will be just 1 over square root of pi x0 under the square root. Now I know my normalized ground state wave function. Well, what about the excited states? The normalized wave function of the excited states. Well, we can just write it down straight away. Nx psi n of x, the wave function of the nth excited state. This is equal to x times 1 over square root of n factorial, a dagger to the power n, acting on the ground state. This is equal to x 1 over square root of n factorial. Well, a dagger is square root of m over 2 h bar omega x plus I p over square root of 2m h bar omega to the power n. Well, I know how each of these operators act in position basis. So psi n of x is nothing but 1 over square root of n factorial square root of m over 2 h bar omega x plus h square root of h bar over 2m omega, derivative with respect to x, you take n of them and act it on psi 0 of x. So we already know what psi 0 of x is. So for any given n, you can just calculate this. But just keep in mind that when you are taking those derivatives, you see the derivative with respect to x doesn't commute with x. You just pay attention to that. Let's calculate psi 1, for example, the first excited state. Now psi 1 of x is equal to, 1 over 1 factorial is 1, square root of m over 2 h bar omega x plus square root of h bar over 2m omega del over del x of 1 over square root of pi x0 e to power minus x squared over twice x0 squared. This is equal to, well, what was h0? x0 is h bar over m omega. Square root of m over 2h bar omega times x over square root of pi x0 e to power minus x squared over twice x0 squared plus square root of x0 over 2, the derivative with respect to x, it will be just 1 over square root of pi x0 multiplied with minus x over x0 squared e to power minus x squared over twice x0 squared. Well, you have certain coefficients. This is just certain coefficients multiplied with x e to power minus x squared over twice x0 squared. You can just work out the coefficient over there. And just add on this psi 1 with that operator over there. Well, this is basically our A dagger operator in position space, position basis. Just act on psi 1 with A dagger. This is psi 1. You get psi 2. Now you can just build all your states. But you see, all the matrix elements, etc., we can already calculate in terms of A and A daggers. So, I mean, this switch to the wave functions most of the time will not be necessary. Now let's do one more thing, and then you are free. You will be free to go. Any questions on this one? Or are you too tired already? Okay, let's stop here. We will continue on Wednesday. Any last minute questions? Yes. Okay. So on Wednesday you will have a question. Okay, so see you on Wednesday. On Wednesday we will, from now on Wednesday we will have 2 hours of lectures, not just one.